In our modern technological society, many people have become reliant on computers. Computers play a dominant role in education, communication, transportation, manufacturing, and healthcare. Computers can perform complex mathematical calculations in a fraction of a second. They can provide data at the touch of a finger. They can perform certain tasks more quickly and more efficiently than a human. And they can even drive our automobiles. Computers can do many things, but few of us ever stop to think about how they operate. How can a machine, which is a collection of wires and circuitry, accomplish all these tasks? In this lab, we will learn a little bit about computers and the languages they use. We will decipher codes written in computer language, and we will even look at some computer programming. As always, before beginning any experiment in the laboratory, be sure you are familiar with laboratory safety requirements. For a demonstration of basic lab safety rules, you can watch our video entitled Lab Safety. To help us understand a little more about how a computer works, let's compare a person driving an automobile with a computer that operates a self-driving or autonomous vehicle. While driving along a road, a person uses his or her senses to perceive the conditions of the road ahead. Impulses from the driver's sensory organs are sent to the person's brain. What happens when those senses detect that a traffic light ahead has turned red? When the driver sees a red traffic light ahead, his brain compares that information with information in his memory of what to do when a red light is encountered. From experience, the driver has learned that when a traffic light turns red at an intersection ahead, he must stop his vehicle before entering the intersection. Then, when the light turns green and no obstructions, such as pedestrians or other vehicles are in the intersection, he can resume driving. Now, let's look at an autonomous vehicle. While driving along a road, an autonomous vehicle uses sensors, such as cameras, radar, and lasers, to perceive the conditions of the road ahead. Signals from those sensors are sent to the vehicle's computer. What happens when those sensors detect a red light ahead? Based on its programming, the computer sends instructions to the vehicle to slow down and come to a stop. Then, when the sensors report that the light has turned green again, the computer programming sends a command to the vehicle to resume driving. A computer acts according to its programming, but what exactly is a computer program? A computer program or application is a series of instructions written in a programming language that a computer follows to complete a task. A computer uses 3 levels of programming languages: machine code, assembly language, and high-level programming languages. Why does a computer need 3 levels of programming languages? The computer's hardware understands only machine code. Machine code is the elementary language of a computer that communicates directly with the computer's hardware to control its operation. The term hardware refers to any of the physical parts of a computer that contribute to a computer system. A major component of a computer's hardware is its central processing unit, or CPU, which is its control center where data is processed and the operating system is run. Hardware also includes peripheral devices such as a keyboard, mouse, camera, modem, video monitor, printer, or speaker. Machine code is written in binary, which is a numerical system that uses only 2 digits, 1 and 0. Each digit in machine code is called a bit of data. Bits of data are arranged in groups of 8 bits. which is called a byte. Machine code is difficult for programmers to read. It is also easy for programmers to make mistakes when writing long strings of numbers in binary. To avoid these issues, programmers use high-level programming languages, which are easier to read and understand. High-level programming languages use letter and number codes that resemble human languages. Some examples of high-level programming languages are Python, JavaScript, Visual Basic, and C++. High-level programming languages interact directly with humans. Machine code interacts directly with computer hardware. However, machine code cannot directly communicate with high-level programming languages. To bridge the gap between high-level programming languages and machine code, assembly language is used. Assembly language is a programming language that uses symbolic codes to represent machine code. To illustrate the 3 levels of programming language, we'll begin with this portion of a simple program written in a high-level programming language. Notice that the program uses words such as string, enter, serial, and print. These instructions are easy for a programmer to learn and remember. When this program is downloaded to a computer, an application called a compiler converts the program into assembly language. Here is a portion of that same program written in assembly language. The code for assembly language is written using letters and numbers that are abbreviations for longer commands. A small portion of the same program looks something like this in machine code. Machine code contains not only bytes of data that represent certain characters, such as letters or numbers, it also contains commands that tell where each character is to be placed in the memory of the computer, as well as the instructions on how to process each character. Each line of code in assembly language becomes many bytes of data written in machine code. All of the programs of a computer, whether they are written in high-level programming languages, assembly language, or machine code, make up the software of a computer. Software is the set of instructions, data, or program applications used to operate the computer and perform specific tasks. The instructions included in machine code might tell the CPU to move the code for a character to a particular spot in the computer's memory to be used later in an application. The type of computer memory that temporarily holds data is called random access memory, or RAM. The instructions might tell the CPU to send a signal to the monitor to darken pixels on the screen to display characters. Or they might tell the CPU to send a signal to a printer to print. Earlier, we said that machine code uses the binary numbering system, which contains only ones and zeros. But in reality, the only 2 things a computer understands is on and off. When the computer receives an instruction containing a number 1 from a program in machine code, current briefly flows through the computer's central processing unit to turn on a piece of hardware. When the computer receives an instruction of binary 0, the current stops flowing. The numbering system we use for everyday counting is the decimal system, which uses the digits 0 through 9. The binary numbering system uses only the digits 1 and 0 to represent numbers. Here are the binary equivalent numbers of the decimal numbers 0 through 9. Computers read bytes of data, so binary numbers are represented by 8 digits in machine code. If we look at this table, we can see how the decimal numbers 0 through 9 are written in machine code. The computer also uses bytes of data to represent letters of the alphabet. Here we see the letters A through J written in machine code. The process of writing, editing, or translating computer code is called coding. Let's try an experiment with coding. For this experiment, we will display a coded message using open and closed circles to simulate machine code. A byte of data is represented with 8 circles. An open circle represents an open switch, meaning that electric current is off, which is indicated with a 0 in machine code. In this example, all 8 circles are open, indicating 8 zeros. A closed circle represents a closed switch, meaning that electric current is on, which is indicated with a 1 in machine code. In this example, all 8 circles are closed, indicating 8 ones. Here are the codes for all 26 letters of the English alphabet, plus the code that instructs the computer to place a space between words. The space character indicates that we have come to the end of a word. The code for the message looks like this. The actual machine code would be more than twice this long, because it would also contain instructions for each character. But we will include only the codes that represent the characters of the message. Let's find the first letter together. Trying to compare the code of the first letter with each code in the chart could be quite time-consuming. Instead, look for patterns that can be matched. Notice that the last 3 circles of this code are closed. When we compare this to the chart, we see that only 2 letters, G and W, have this pattern. Once we know that, it is easy to see that G is the correct answer. Now, pause the video and translate the rest of the code. How did you do? If you were successful in translating the code, you will have spelled out the traditional greeting, "Good day." Now that we have had some practice reading a message in machine code, we can use that knowledge to translate another message. However, this time, instead of using circles, we will be using LEDs to spell out the code. The LEDs will be part of a digital display that we will assemble. After we construct the digital display, we will take a brief look at the programming code that will be used to produce the message. The digital display will be constructed on a breadboard using jumper wires, LEDs, resistors, and a microcontroller. A microcontroller is a simple computer contained on a single integrated circuit board. The CPU is contained in an integrated circuit in the center of the circuit board. The CPU receives power and programming from another computer through a cable connected to a port attached to the end of the circuit board. Around the perimeter, on 3 sides of the circuit board, are tiny connectors called pins that can send and receive signals to and from peripheral devices. We will use the digital pins numbered 2 through 9 for our digital display. Here is one of the circuits of the digital display. A cable carrying electric current from a laptop computer is connected to the microcontroller. For this circuit, a red jumper wire will carry current from pin number 2 on the microcontroller to the breadboard. Current will then flow through an LED. An LED cannot handle a large voltage, so a resistor in each circuit will prevent the LED from being overloaded. From the resistor, current will flow through a blue jumper wire to the negative power bus of the breadboard. A black jumper wire will carry current from the negative power bus to a pin called a ground pin on the microcontroller. From the ground pin, current will flow back to the computer. A program written in a high-level programming language will instruct the microcontroller to send a signal through the circuit to turn the LED on and off. Look at the code in line 3 of this program. The word pin mode tells the microcontroller that we want to do something with the circuit connected to one of the pins on the microcontroller. The 2 in parentheses tells us that we are using pin number 2. The word output tells the microcontroller that we want to send a signal from pin 2 to the circuit. The code in line 4 of the program includes the instruction digital write with the number 2 in parentheses. This instruction tells the microcontroller to send a digital or binary command to the circuit connected to pin 2 of the microcontroller. Binary commands can be only on or off. So the digital write command will either turn the current on or off. The word high and the number 2 in parentheses tell the microcontroller to turn on the electric current from pin 2, which is connected to the circuit on the breadboard. When we run the program, it turns on the LED. Unless we provide the microcontroller with some additional instruction, the LED will remain on indefinitely. So, we will add an instruction to turn off the LED. Line 5 of the program uses the command digital write again, but this time we use the word low in parentheses. This tells the microcontroller to turn off the current to pin 2. Let's run the program with the additional instruction. It appears as though nothing happened. What went wrong? Since the computer can process millions of lines of code in a second, the microcontroller turned the LED on and then turned it off in a millisecond, which is too quick for our eyes to perceive. To fix that problem, we need to tell the microcontroller to add some time to the high command. We do that with a delay command before the microcontroller turns off the current. The computer understands time in milliseconds, so we set the time delay for 500 milliseconds, which is 1/2 or 0.5 seconds. In this way, the microcontroller will allow current to flow into the circuit for 500 milliseconds before it turns off the current. Let's run the program again. This program runs once and then ends. If we want the program to run continuously, we need to move some of the instructions. There is a line in the program that says void loop. Any instructions written below that line in the program will loop or repeat until specifically told to stop. Here we have moved the digital write and delay instructions below the void loop line. However, we must add one more line of code that adds a delay after the microcontroller turns off the current and before it runs the program again. Let's run the program and see what happens. The program runs repeatedly, causing the LED to light up, turn off, and then light up again. Here is the breadboard with 8 circuits in place. Each circuit has an LED. Each LED represents 1 bit of data. All 8 LEDs represent a byte. Each circuit is connected to a separate pin on the microcontroller so it can be controlled independently of the other circuits. To test the circuits, we will run a program that will light up each of the LEDs in sequence. Notice that all the LEDs shine with green light. 6 LEDs have green covers and shine with green light. 2 LEDs have clear covers, but they still shine with a green light. LEDs do not shine green because of their covers. They shine green because their LEDs emit light at the frequency and wavelength of green light. We used the clear LEDs to indicate the first and last bits of each byte. Using the 8 LEDs on our digital display, we will spell out a short 5-word message that you will translate from binary into English. The simple program we used earlier to turn on and off one LED required 11 lines of code. However, the program that displays our short message required nearly 1,000 lines of code. When we run the program, it displays the message like this. All 8 LEDs light up to signify the beginning and the end of the message before it repeats. To translate the message from machine code into English, we will greatly slow the message. Here is the first letter of the message. The LEDs for this byte are from left to right, off, on, off, 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 on, on. Compare this sequence with the chart of code for the letters of the English alphabet, like we did earlier in the lab. The sequence matches the pattern for the letter G. Here is the second letter of the message. Notice that the LED pattern for this letter is off, on, off, off, on, on. Determine the letter by comparing the lights with the machine code chart. At any point, pause the video if you need more time to translate the code. Here is the third letter of the message. The LED pattern is off, on, off, 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 on, off. Determine the letter by comparing the lights with the machine code chart. Here is the next character of the message. This character represents a space, which means this is the end of the first word of the message. Here is the first letter of the second word. Here is the second letter of the second word. A space means this is the end of the second word of the message. The third word has 6 characters. Here is the machine code for the first character. Here is the machine code for the second character. Here is the machine code for the third character. Here is the machine code for the fourth character. Here is the machine code for the 5th character. Here is the machine code for the 6th and final character of the third word. The next word in the message is another short word with only 4 characters. Here is the machine code for the first character of the 4th word. Here is the machine code for the second character. Here is the machine code for the 3rd character. Here is the machine code for the final character of the 4th word. We just have one last word to translate. Here is the machine code for the first character of the final word of the message. Here is the machine code for the second character. Here is the machine code for the 3rd character. Here is the machine code for the 4th character. Here is the machine code for the 5th character. And here is the machine code for the final character of the final word. If you translated the message correctly, you have the greatest message ever given to the world. God so loved the world. This message is part of John 3:16 in the Bible that says, "For God so loved the world, that he gave his only begotten Son, that whosoever believeth in him should not perish, but have everlasting life." At this time, proceed with the corresponding activities.